In this module, you will be introduced to the basic physical principles of hydraulics. A knowledge of the basic physical principles will help you to understand how hydraulic components, hydraulic systems and hydraulic circuits work. The individual learning units are reinforced by simple sample calculations with realistic values. The following learning objectives are to be achieved with this learning module. You should be able to understand the basic relationship between mass and force and be able to calculate forces. You should be able to calculate the pressure in a hydrostatic system. You should be able to describe Pascal's law. Force, displacement and pressure transmission in hydraulic components are a result of Pascal's law. You should be able to calculate force, displacement and pressure. You should be able to understand the purpose and meaning of the physical unit, PSI. You should be able to explain the difference between absolute and relative pressure and be able to calculate them. You should be able to calculate flow rate and flow velocity. You should be able to evaluate different types of flow and be able to calculate them. You should be able to explain the cause of flow rate in a hydraulic system and describe the ways of controlling it. In everyday life, the word force can have a variety of meanings. In physics, however, the concept of force is very clearly defined. Force is the ability to change the state of motion of a body. In other words, the action of a force on a body causes the body either to accelerate, to decelerate or to move in another direction. A force is also able to change the shape of a body. For the present, however, we will not consider this particular effect. We will start by considering force only in relation to rigid, thus non-deformable bodies. In physics, increases in speed, braking and changes in direction are all examples of acceleration. Force is therefore related to acceleration. Thus it stands to reason that the greater the force applied, the greater the acceleration to which the body is subjected. At the same time, force is also related to the mass of the body on which it acts. The greater the mass of the body, the greater the force required to accelerate the body. This concept gives us the well-known formula, force equals mass times acceleration. The imperial unit of force is pound, in short, lb. The SI unit of force is the Newton, in short, N, named after renowned physicist, Sir Isaac Newton, who first formulated the relationship between force, mass and acceleration. We can also use the formula to determine weight. If air resistance is not taken into account, we note that all bodies are pulled towards the Earth with the same acceleration. This is known as the acceleration due to gravity and in short, g. Acceleration due to gravity is not equal everywhere on the Earth, but on average it is 32.2 foot per square second. If we now put the body onto a surface, the surface must oppose the acceleration due to gravity. The mass of the body multiplied by the acceleration due to gravity is therefore the force which the body exerts upon the surface, i.e., its weight. A mass of one slug exerts a force of 32.2 pounds on the Earth's surface. Let us consider a container filled with a liquid. We now close the container with an appropriately sized piston. If we now apply a force, by means of the piston, to the liquid enclosed in the container, hydrostatic pressure is created. Pressure is an important variable when describing operations with liquids. The amount of pressure, P, in the enclosed liquid depends on the applied force, F, and on the surface area, A, of the piston. It is independent of the amount of liquid, the size or shape of the container, or the type of liquid. It stands to reason that the greater the applied force, the greater the resulting pressure. Any increase in the surface area to which the force is applied will bring about a reduction in the pressure. This relationship provides us with a formula to calculate static pressure. Pressure is the ratio of the force to the applied area. The imperial unit derived from this for pressure is pounds per square inch, or in short, PSI. 1 pound force acting on 1 square inch of area will produce 1 psi. The derived SI unit of pressure is the Pascal, or PA. Blaise Pascal, a great philosopher and scientist, was the first person to undertake intensive studies of hydrostatics. In practice, the unit, bar, is generally used in the metric system to express values of pressure. 1 bar corresponds to 14.5 psi. Let us look at the simple sample calculation. A hydraulic cylinder with a piston diameter of 2 inches contains liquid at a pressure of 2000 psi. We need to know the force exerted by the piston. In order to solve the problem, we must first rearrange our formula, P equals F divided by A, in order to separate the required variable. We obtain the area of the piston from its diameter using the formula for the area of a circle. If we now input the value of the area of the piston into our original formula, we are able to calculate the force and solve the problem. The way in which liquids and solid bodies transmit force is different. In this example you can see a load arranged on a fixed mounting. The mounting transmits the weight in one direction only, downwards. If we place the load on the movable lid of a container filled with liquid, the weight is acting on the liquid and pressure is generated within it. However, the pressure generated not only acts directly downwards, but is spread equally throughout the liquid in all directions. The pressure always acts perpendicular to the walls of the container. The value of the pressure, P, within the liquid is equal to the force, F, relative to the effective area, A. If the gravitational pressure of the liquid is neglected, the pressure at every point in the liquid is equal. Neglecting the gravitational pressure makes sense, since the pressures normally encountered in modern hydraulic equipment are normally of a much higher order than the gravitational pressure. Pascal's law is thus defined. When a force is applied to a stationary liquid, it causes a pressure inside of the liquid. This pressure is then transmitted equally in all directions throughout the liquid. This is the basic principle of hydrostatics. Since the pressure is distributed equally in all directions, the shape of the container isn't important. In the same way, if we took two such containers and combined them together, the same pressure would still act throughout. Let's look at what conclusions can be drawn from the above. A force F1 acting on surface area A1 generates a pressure P1. Pressure P1 acts equally at every point throughout the system, including surface area A2. Therefore, pressure P1 is equal to pressure P2. Pressure is force divided by applied surface area. Therefore, F1 divided by A1 is equal to F2 divided by A2. By rearranging these equations we obtain F1 over F2 equals A1 over A2. Or we can express it like this: the ratio of the forces is equal to the ratio of the areas. This leads us to the conclusion that for any given pressure, the greater the surface area, the greater the force. A hydrostatic system, such as the one shown here in the diagram, may therefore be used for the transmission of force. This example demonstrates the effectiveness of the force transmitted. The diagram shows a hydraulic elevator set up to raise an elephant. The effective surface areas are 10 square inch and 300 square inch respectively. We need to know the necessary force to be applied in order to lift the elephant. In order to solve the problem, we must rearrange our formula for pressure equilibrium in order to isolate the required variable. Calculating, we obtain the value of F1, 100 pounds. Let's look more closely at how the force is transmitted by the lifting device. A force is applied to the smaller piston. This force divided by the surface area of the small piston generates pressure. The load is lifted by liquid being moved from the small to the large cylinder. Exactly the same amount of liquid is received into the large cylinder as is removed from the small cylinder. The volume of the liquid removed from the cylinder on the left amounts to the surface area of the small cylinder multiplied by its displacement. The volume of the liquid provided for the cylinder on the right equals the surface area of the large cylinder multiplied by its displacement. Both of these liquid volumes V1 and V2 are identical. Rearranging the equations gives us S1 over S2 equals A2 over A1. Or put into words, the piston displacements are inversely proportional to their respective surface areas. We can therefore now state that for a given displaced volume of liquid, the smaller the piston's surface area, the greater the stroke. A hydrostatic system, such as the one shown here schematically, is able to transmit displacement. This is the principle of the hydraulic elevator. This simple example illustrates how the displacement transmission is achieved in hydraulics. Consider a hydraulic elevator having piston surface areas of 10 square inch and 300 square inch. The larger piston has a stroke of 100 inches. We need to know the length of travel of the smaller piston. To set about solving the problem, we first rearrange our formula for volume equilibrium to isolate the required variable. We are left with a piston displacement value S1 of 3000 inches. We have previously been looking at how force is transmitted hydraulically between two pistons. The forces have been applied to the system or transmitted from it by mechanical elements such as the piston rods. We now look at the concept in another way. Two pistons of different sizes are connected by means of a rigid bar. Under the application of pressure P1 on surface area A1, force F1 appears. Force F1 is transmitted by the bar to the surface area of the smaller piston A2, giving rise to pressure P2. The forces F1 and F2 are in equilibrium. Thus, F1 equals F2 and P1 times A1 equals P2 times A2. Rearranging this formula gives P1 over P2 equals A2 over A1. Putting this into words, the ratio of the pressures is inversely proportional to that of the piston surface areas. We are now able to state that, for any given force, the smaller the surface area, the greater the pressure. Hydraulic components, such as the one shown in the diagram, are designed to transmit pressure. Again, a simple calculation for this. Given a hydraulic intensifier having piston surface areas of 10 square inch and 1 square inch, the inlet pressure P1 equals 3000 psi. What will be the value of the exit pressure P2? To solve the problem, we must first rearrange our formula for force equilibrium in order to isolate the required variable. The calculation results in a pressure value of P2 of 30,000 psi. This concept is used in industry, in particular in the process known as hydroforming, in which components are deformed under the application of very high pressures. The effect can also work in negative sense, for example with so-called differential cylinder with a single piston rod. If the volume of fluid displaced from the annular area on the side of piston rod faces a resistance such as a flow control valve proportional to the areas, it is possible to cause high excess pressure on the rod side of the piston. Of pressure psi is very frequently encountered as a measure of pressure in the imperial system, not only in this module but in hydraulics generally as well as in everyday life. We need to understand what 1 psi actually means and how it relates to other units. PSI is actually an acronym for the unit pounds per square inch and is the pressure which is generated when a force or weight of 1 pound acts on a surface area of 1 square inch. In the metric system we typically see pressures measured in bar. Although bar is not an official SI unit, it is commonly used and may therefore be used in technical data in accordance with EU directive. The actual SI unit for pressure is the Pascal. However, it is a very small unit. For this reason bar has become the established unit for pressure. 1 bar corresponds to 100,000 Pascal or 14.5 psi. The actual name bar does not relate to a renowned scientist as does the Pascal or the Newton, but is instead derived from the Greek word baris, meaning heavy. The air pressure is an effect of the gravitational force which also is applied naturally on the atmosphere. Pressure caused by gravity is also created by a liquid in a container. Imagine a container in the form of a 12-inch cube and therefore with a base area of 144 square inch. The volume of the container is therefore 1,728 cubic inch or 1 cubic foot. Water has a density of 62.4 pounds per cubic inch. This means that 1 cubic foot of water has a weight of 62.4 pounds. If we were to now calculate the pressure that the water generates on the floor under the cube, that pressure would be approximately 43 psi. Let us now take 34 such cubes and stack them one upon the other. The weight force is now multiplied by 34, whilst the base area remains the same. The pressure is therefore multiplied by 34 and now amounts to 14.7 psi. One standard atmosphere is therefore equivalent to 34 feet of water. Let us take a second column with 34 cubes, place it beside the first and calculate the pressure on the floor. The weight force has doubled, but so has the area. The pressure therefore remains the same. However, were we to place the second column on top of the first column, the pressure would then be doubled. If we were to cut our 34 feet water column in half lengthwise and then remove one half, half of the weight force would remain, as well as half of the surface area. The pressure on the floor is still 14.7 psi. A 34 feet high water column therefore always generates a pressure of 14.7 psi or 1 bar atmosphere regardless of how much water is in the column, or the actual size of the container. Accordingly, a 340 feet high water column always generates a pressure of 147 psi. A pressure of nearly 6,000 psi would be generated by a column 14,000 feet high, etc. The hydraulic cylinder of this forklift truck has a working pressure of 3,000 psi, whilst the truck's tire pressure is 50 psi. The air in a warehouse is at standard atmospheric pressure, i.e., 14.7 psi. These pressure values are not directly comparable, since they are values taken from different points of reference. The pressure of the air in a warehouse is due to the gravitational pressure of the atmosphere. If there were no atmosphere, there would be no pressure. The reading on a barometer would be 0. If we measure the pressure against zero pressure in an empty room, then we are talking about the absolute pressure, in short, P, absolute. If the tires of the forklift truck are not pumped up, then the pressure inside the tires would be the same. Absolute pressure as in their surroundings, i.e., 14.5 psi. If we pump up the tires, the absolute pressure in them increases. The difference between the pressure in the tires and the pressure in the surroundings is known as the gauge pressure psi, G. This gauge pressure is the value we typically express when stating pressure levels in the hydraulic circuit and therefore is normally stated simply as psi. The relationship between absolute and gauge pressure is, therefore, gauge pressure equals absolute pressure minus 14.5 psi. Absolute pressure is often distinguished by the unit psi, or psi absolute. The pressure values in the hydraulic cylinder and the tires of our forklift truck are measurements of gauge pressure. In other words, the absolute pressure in the hydraulic cylinder is, in fact, 3014.5 psi, whilst in the tires it is 64.5 psi. Occasionally, we come across the concept of negative relative pressure, for example in a vacuum cleaner. The relative pressure we are then referring to is known as negative pressure or pressure less than atmospheric pressure. Here is a simple sample calculation for this concept, given a simple hydraulic circuit. A hydraulic pump draws liquid from a container and supplies it to a hydraulic cylinder. The relative pressure on the inlet side of the pump measures minus 3 psi. we need to find the absolute pressure in the suction pipe. In order to solve the problem, we first rearrange our formula to isolate the required variable. Calculating, we get an absolute pressure of 11.5 psi in the suction pipe. This can also be expressed as a negative pressure of 3 psi. In those cases where the pump inlet is located above the level of the fluid, attention must be paid to the value of pressure prevailing at the pump inlet. This pressure should not be too low, in order to avoid such negative effects as cavitation. Another physical variable which we require for the better understanding of hydraulic systems is the flow rate. Flow rate tells us how much fluid is flowing through a system in a given time interval. Flow rate is, therefore, the relationship of volume V versus time t. The associated symbol is QV. Let us consider a container with a known volume. We now fill the container from a tap and we measure how much time that takes. From the known values of volume and time we can now calculate the flow rate of the liquid through the tap. There is another method of establishing flow rate that can be used for cylindrical containers, a pipe with a constant cross-sectional area, for example. In this case, we consider the cross-sectional area of the moving fluid A and we record the velocity at which this fluid is flowing. This velocity is known as the flow velocity V. The flow rate QV is now given by the product of the flow through cross-sectional area A and its flow velocity V. In hydraulics, flow rate is normally given in units of gallons per minute, whilst cross-sectional area is measured in square inch and flow velocity in inch per second. The use of a correction factor in the controlling formula saves us having to recalculate the units every time. Using this formula, the flow rate is automatically computed in gallons per minute, provided the values for cross-sectional area A and average flow velocity V are put into the formula in square inch and inch per second respectively. A simple example demonstrates. Given is a hydraulic cylinder being supplied with a flow rate of 20 gallons per minute. The piston area is given as 200 square inch and the piston displacement measures 100 inches. We need to know the time required by the piston to move through its stroke. To solve, we first rearrange our formula to isolate the required variable. We obtain the volume using the known values of piston stroke and cross-sectional area. Knowing that there are 231 cubic inch in 1 gallon, this volume can be converted to 86.5 gallons for the calculation. The time taken is calculated to be 4.32 min. In this module, you have learned the application of Pascal's law in the hydraulic elevator. The volume, which is being displaced from one side, will be supplied at the other side, independent of the type and cross-section of the container and the pipes. Let us apply this concept to a pipeline with a changing cross-sectional area. Whilst the fluid is flowing through the pipe, there is no interruption to the flow. In other words, the same volume is flowing everywhere within the pipe over the same time period. The flow rate is the same throughout. The flow rate QV is the same throughout the length of a pipe. If a pipe has different cross-sectional areas A1 and A2, two separate values of flow velocity must develop in each cross-section. The flow rate formula allows us to calculate these two separate flow velocity values. The flow rates in the two separate pipe sections are given by Q V1 equals A1 times V1 and Q V2 equals A2 times V2. However, we have already established that the flow rates in both sections of the pipe are equal. Thus, A1 times V1 equals A2 times V2. Rearranging this formula gives us V1 divided by V2 equals A2 divided by A1. Or putting it into words, the ratio of the flow velocities is inversely proportional to that of the cross-sectional areas. Flow type is another very important fluid flow property and one which is dependent upon the flow velocity. There are two types of flow: laminar and turbulent. Fluids moving at low velocities demonstrate laminar flow characteristics, i.e., the fluid flows in layers through the pipe. The inner fluid layer is moving with the greatest velocity, whilst the outermost fluid layer in contact with the walls of the pipe has virtually no velocity and is almost stationary. There is no mixing between the layers and no eddies or cross flows are formed. This type of flow results in only minimal losses of energy and pressure. If the flow velocity is increased to a critical value, the nature of the flow begins to change. Eddies are formed within the flow, which can lead to a complete mixing of flow lines. This type of flow is known as turbulent flow. Turbulent flow results in increased flow resistance and, as a result, increased hydraulic losses. The transition from laminar to turbulent flow usually results in large pressure losses. Turbulent flow, therefore, is something to be avoided in hydraulics. The type of flow that will take place in a smooth, straight pipe having a circular cross-section can be very well determined. The so-called Reynolds number should be determined for this. The Reynolds number is equal to the flow velocity times the pipe internal diameter, divided by the kinematic viscosity of the fluid. The result is a dimensionless number. The threshold or critical value for the crossover between laminar and turbulent flow is set at approximately 2300. A Reynolds number below the critical value denotes laminar flow. A value above the critical value denotes turbulent flow. The transition from laminar to turbulent flow usually results in large pressure losses. Turbulent flow, therefore, is something to be avoided in hydraulics. The type of flow that will take place in a smooth, straight pipe having a circular cross-section can be very well determined. The so-called Reynolds number should be determined for this. The Reynolds number is equal to the flow velocity times the pipe internal diameter, divided by the fluid's kinematic viscosity of the fluid. The result is a dimensionless number. The threshold or critical value for the crossover between laminar and turbulent flow is set at approximately 2300. A Reynolds number below the critical value denotes laminar flow. A value above the critical value denotes turbulent flow. To solve the problem, we must first calculate the flow cross-sectional area A. In order to find the flow velocity V, we need to rearrange the flow rate controlling formula. Inputting our value for A now gives us a value for the flow velocity. We now have all the property values we need to calculate the Reynolds number. The value of Reynolds number calculated is greater than the critical value of 2300. Hence we conclude that the flow through the pressure pipe is turbulent. One option to convert the flow in this particular example into a laminar flow would be to use a pipe with a larger internal diameter. As an additional exercise, you can, if you so wish, calculate the minimum internal pipe diameter required to achieve laminar flow. In practice, however, there is no need to check mathematically whether the flow will be laminar or turbulent for each and every pipeline. Often the system is designed using experience values. Here you can see some of those values based on experience for the permissible flow velocities, which help to prevent higher pressure losses. This example shows how experience values can help in the testing of a pressure pipe. Given a 0.625 by 0.125 inch, hydraulically smooth pressure pipe with an anticipated flow rate of 5 gallons per minute. Only the flow velocity V needs to be calculated to determine the type of flow. To solve, we start by calculating the flow cross-sectional area A and the flow velocity V. The value of 174.8 inch per second lies below the previously determined critical flow velocity and therefore indicates that the expected flow will be laminar. In this module, You will learn that force is the cause of motion. Further, we will be discussing the most important physical variables in hydraulics, namely pressure and flow rate. We should now consider how these three physical properties are interrelated. Let us consider any portion, randomly chosen, of a certain quantity of fluid in a pipe. As long as no force is acting on it, the fluid will remain stationary. The fluid will continue to remain stationary if equal but opposing forces are acting upon it. Movement will only begin when a force acting on one side of the fluid is greater than the force acting on the other side of it. So, for a pipe with constant cross-sectional area, the prerequisite for flow rate is therefore a pressure difference within the pipe itself. If we introduce a restriction to the flow of a fluid in the form of change in cross-sectional area, this will result in a loss of pressure at the narrow point. In fact, restrictions are often used in hydraulics, in order to reduce volume flow. Such components are known in hydraulics as throttle valves. They are used in combination with pressure valves to control flow rate, and in applications such as a hydraulic elevator. We must differentiate between two construction principles, the orifice and the throttle. From the point of view of construction, it can be noted that the throttling length of an orifice is very short in comparison to that of a throttle. This means that the viscosity of the hydraulic fluid has less of an influence on the flow rate across an orifice than it does in the flow rate across a throttle.